welcome to this video on the applications of partial fractions to integration. Doing this video today, I'm assuming that you've already gone through the Year 11 Specialist Maths course, and so I've already had the introduction to partial fractions there. However, as you can see on screen at the moment, I have still summarized the notes there, so if you need those, you can sort of add them to your book. But I guess there's one critical thing, and that is that if you are given an improper fraction, which is where the power of the numerator is greater than or equal to the power of the denominator, we need to use long division first to simplify it. And then from there we'll end up with a fraction as the remainder, in which we can use the partial fractions on. So I'm just going to leave this here on screen for a minute and basically suggest that you add those couple of notes there. But basically for each linear factor, let's say it's x minus a in the denominator, then there'll be a partial fraction of the form a on x minus a. For a repeated linear factor, x minus a squared, for example, then partial fractions of the form b on x minus a and c on x minus a all squared exist. This pattern actually continues for further powers. So, if we had a power of 3 there instead, then we'd also have a d on x minus a cubed fraction. But for the purposes of this course, we only need to worry about going up to powers of 2. And then thirdly, for each irreducible quadratic factor. So irreducible means that it can't be factorized. Then there'll be partial fractions, or there'll be a partial fraction of the form dx plus e on that quadratic. Okay. So just going to scroll down and we'll have a look at the questions. Oh, this doesn't seem to be working. Just give me a minute. Right, I've got it working now. So just got this first question here. Evaluate the integral of 2x squared plus 15x plus 45 all over x squared plus 25 times 3x minus 1. So to begin with here, what I'm going to do is I'm going to break this into its partial fractions, and I'm just going to say that all that mess, the 2x squared plus 15x plus 45 all over x squared plus 25 3x minus 1 must be equal to, now we have a single linear factor there, the 3x minus 1. So that's going to be possible to break it into a on 3x minus 1. Plus, then we have an irreducible quadratic factor right there, the x squared plus 25. So that can't be factorized over the real numbers. So our partial fraction there is bx plus c over x squared plus 25. Now, if I make a common denominator here, so by multiplying each fraction by the denominator of the other, then I can say that 2x squared plus 15x plus 45 is going to be equal to a times x squared plus 25 plus bx plus c multiplied by 3x minus 1. And from here we just need to figure out what a, b and c are. So I'm going to start off by making x equal 1/3. Now, just so you know, an approach that I could take would be to expand it all out and then compare the coefficients, but I think this is perhaps a nicer way to begin with. So if we make x equal 1/3, that's going to make this bracket here just equal 0. We know that 0 times bx plus c is going to still be 0. So that leaves us with, now remember I've got x equal to 1/3, so I've got 2 times 1/3 squared plus 15 times 1/3 plus 45 equals a times 1/3 squared plus 25. Hopefully this won't be too bad to evaluate. So we've got 2/9 plus 5 and then plus 45 equaling a times 1/9 plus 25. And just evaluating this now, so we've got 2/9 plus 50, so that's going to be 452 on 9. And on the right hand side, 25 is the same as 225 on 9, so 226 on 9a. And we can see right away that the 9s are going to cancel each other out. If we divide by 226, then the 452 over 226 just goes to 2. And so we get a equals 2. That's pretty nice. Now, from there, we could figure out what B and C are by using simultaneous equations. We could make x equal literally whatever values we want them to be. Perhaps you could consider making x equals 0, because that would then cancel out the b term. However, that does still leave the a part at the front, which is a little bit annoying, but you know, we know what a is anyway, so that's all right. We could work with that. But actually, rather than doing that, I'm just going to compare these now. Because we know that a is 2, that means that right here, we're going to get a 2x squared term. And you notice here that we have a 2x squared term. So that means that any other term which gives me an x squared on the right-hand side has to have a coefficient of 0. And that's going to come from having bx times 3x. That would give us 3bx squared. So because I want that to be 0, then I know that b must equal 0. So a nice way to do that one just by comparing them. So if b equals 0, then on my right hand side I've really got 2x squared plus 50, just from expanding out that first bracket there, and given that we know what a is, and then plus 3cx, and then minus c, equaling 2x squared plus 15x plus 45. So hopefully without too much trouble, we can see that the value of c here is going to be just 5. And the reason for that is that, well, we've got this 3cx term here, and that needs to be equated with this 15x. And so there's no other way we can get an x term on that left-hand side. So c must equal 5. So now I've got my partial fractions. And I can say that 2x squared plus 15x plus 45 all over x squared plus 25, 3x minus 1, is equal to, now, so it's a over 3x minus 1, so that's 2 over 3x minus 1, plus, and then bx plus c, well, b is nothing and c is 5, so it's going to be 5 over x squared plus 25. And so we can do the integral of that much more easily than we could possibly do the one that we had before. So I'm going to just say integral of 2 on 3x minus 1 plus 5 on x squared plus 25 dx is equal to. Now this first one here is going to be a log, okay? And when we have the log, well, we need the numerator to be the derivative of the denominator. So we actually need that numerator to be a 3. Now, what I'm going to do, firstly, is I'm going to take the 2 out the front, and then I'm going to make the numerator a 3, but I can't just make it a 3 without countering that, so I'll put the 3 there. And then we've still got a 3x minus 1 there. And the second fraction just here, well, whenever we've got an x squared plus some constant, we should be wary at least that this could potentially be an inverse tan function, which in this case it is. And it's actually quite a nice one at that. So let me just, I might actually just leave, write that as dx there, and then plus integral of 5 on x squared plus 25 dx. So that gives us 2/3 log e of the modulus of 3x minus 1. And then we've also got plus inverse tan of x on 5. And we can't forget the plus c. So there we have it. Worked out quite nicely. Now, the reason that that occurred was because in this one here we didn't have an x term. If we happen to have an x term there, it would actually also be a log, but we'll probably see that in the next example. So if we scroll down just a little bit, this was a question taken from the 2017 VCAR Specialist Exam 1, and this was just question 2 on the exam, so relatively early and should be relatively straightforward. Find the integral between 1 and root 3 of 1 on x times 1 plus x squared dx, expressing your answer in the form log e of root a on b. Okay, so first things first, I'm going to break that into partial fractions. So I'm going to say 1 over x times 1 plus x squared must be equal to a on x plus, and then, so that's the first linear factor there. Then we've got an irreducible quadratic here as well, so that's going to be bx plus c on 1 plus x squared. So by the same process as we had before, I'm going to just equate the numerators, and again I have to use my cross multiplication on this side, so I'm going to get a at the front of 1 plus x squared plus, I'm just going to expand this right away, bx squared plus cx. So I'm just going to let x equal 0, because that's going to get rid of the b and c terms. And that gives me 1 equals 1a. Well, that was quite nice. Now from there, I can say that 1 equals 1 plus x squared plus bx squared plus cx. So you can see that on the left-hand side there is no x squared term, which means that this b here must be -1, because we need the x squareds to cancel each other out. So I can straight away say b equals -1, and also that c equals 0, because on the left-hand side there is no x term either. And so therefore, we're actually doing the integral of, now it was a on x, so 1 on x minus, and I'll put the minus there because it's plus bx plus c, so minus x plus 0 over 1 plus x squared dx. Wow, this is looking pretty good. So that's going to equal, now 1 on x just straight away becomes log e of x, log e of modulus of x I should say. And I can't forget my terminals either. That was between 1 and root 3. And then I've got minus, now we've got an x over an x squared, so that's the derivative over the original thing. So this is actually going to be a log as well, but the problem is we need the numerator to be 2x. And so to make that a 2, just here, I would need to have a factor of half out the front to counter that. And so I get half of log e modulus of 1 plus x squared. And that's between 1 and root 3. So now we can just substitute our terminals in. We do the upper terminal first. So that's log e of the square root of 3, because modulus of the square root of 3 is just root 3. Minus half log e of, now that's going to just become 4. Minus, and then we sub our other terminal in, we get log e of 1. And then minus half log e of 2. From here we just need to simplify. Now log e of 1 from the log law disappears, okay, because it's equal to 0. So we have log e of root 3. Now half log e of 4, we can move this half to the power here, and so 4 to the power of half is just 2, because it's the square root of 4. So I'm just going to express this as log e of 2, and then I've got plus half log e of 2. And negative log e of 2 plus half log e of 2 is just going to be negative half log e of 2. So log e of root 3 minus half log e of 2. And again, we can move that coefficient there up to the power. 2 to the power of half is square root 2. So we've got log e of root 3 minus log e of root 2. And then finally, using our log laws again, when we're subtracting logs, we divide what's inside them. So we get log e of square root of 3 on 2. And there we have it. We've got that in the form that was required at the beginning of the problem, right there. So there we have it. Anyway, I'll leave that video there. That's a little over 16 minutes, so that's enough time on this. See you in the next one.